Imagine a place where time slows down, where a single hour feels like a century elsewhere. Welcome to the edge of a black hole, nature's ultimate time machine. Here, the fabric of space-time is so warped that gravitational time dilation becomes reality. As you approach the event horizon, time for you ticks slower compared to the universe outside. Could this be a gateway to the future? Join us as we journey through the mysteries of black holes and explore the tantalizing possibilities of time travel. Time is often seen as a constant, but in physics it's much more complex. Time is a dimension, just like space, and is a measure of change and motion. From ticking clocks to the orbits of planets, time governs all motion in the universe. Unlike space, time has a direction, it flows forward. But what if we could change its speed or direction? Understanding time is the first step toward understanding time travel. In 1905, Albert Einstein revolutionized our understanding of time and space with his theory of relativity. He showed that time is not absolute. It's relative to the observer's motion and gravitational field. A moving clock ticks slower than one at rest, a concept known as time dilation. This forms the foundation of modern physics and is key to understanding how black holes can affect time. Time dilation occurs when time passes at different rates for observers in different conditions. For instance, an astronaut traveling near the speed of light ages more slowly than people on Earth. Similarly, strong gravity also slows time. The closer you are to a massive object, the slower time flows. This effect is not science fiction. It's measured by satellites and atomic clocks. Gravity and time are linked through general relativity. Massive objects like Earth or black holes warp space-time, and this warping slows down time. This is why time ticks a bit slower on the surface of Earth compared to outer space. Near a black hole, this effect becomes extreme, a phenomenon known as gravitational time dilation. You don't have to go to space to witness time dilation. GPS satellites, for instance, experience both speed-based and gravity-based time differences. Their clocks tick faster than those on Earth due to weaker gravity and slower due to their high velocity. Engineers correct for this daily, proving that relativity isn't just theory, it's practical and real. Space and time are part of a unified concept called spacetime. Think of it as a 4D fabric that can be stretched, bent, or twisted. Massive objects like stars or planets create dents in this fabric, influencing how objects move and how time flows. Understanding spacetime is crucial for grasping how black holes and time travel might work. When we say spacetime curves, we mean that both space and time are affected by mass and energy. A marble on a trampoline mimics how planets bend the fabric. Light bends, clocks slow, and objects follow curved paths. In extreme cases, like near a black hole, this curvature becomes so steep that time nearly stops. Time warps are more than science fiction. By simulating space-time distortions, scientists visualize how time and gravity interact. Visual models show steep wells where gravity is strong, indicating how time slows. These models help us understand extreme environments like neutron stars and black holes. A black hole is an object so massive and dense that nothing, not even light, can escape its gravity. It's the ultimate warper of space-time. At its edge, the event horizon, time slows to a crawl. Step across it, and you might never come back. But this extreme time dilation also opens the door to future time travel. A black hole has three main parts: the event horizon, the photon sphere, and the singularity. The event horizon marks the point of no return. The photon sphere is where light orbits the black hole, and at the center lies the singularity, a point of infinite density and zero volume, where all known laws of physics break down. Black holes are born when massive stars exhaust their nuclear fuel and collapse under their own gravity. If the remaining core is heavy enough, it shrinks into an infinitely dense point. This process can happen in seconds, creating a region from which not even light can escape. Some black holes also form from collisions of neutron stars. The event horizon is the spherical boundary around a black hole. Once crossed, escape is impossible. From an outside perspective, anything nearing this boundary appears to freeze in time due to extreme time dilation. However, to the falling object, it crosses the horizon without noticing anything unusual. At the core of a black hole lies the singularity, where gravity crushes matter into an infinitely small point. Physics, as we know it, cannot describe this state. Space and time cease to exist in their normal form. Some scientists believe quantum gravity might one day explain what happens at this point. Before falling in, matter often forms a hot, spinning accretion disk around the black hole. Friction in the disk creates intense heat and light, sometimes outshining entire galaxies. Studying these disks helps astronomers detect black holes and understand their behavior. There are different types of black holes: stellar mass, intermediate, and supermassive. Stellar mass black holes form from dying stars. Supermassive ones, millions to billions of solar masses, reside at galactic centers. Intermediate black holes are rarer and harder to detect. Each type offers different insights into cosmic evolution. At the heart of most galaxies lies a supermassive black hole. Our Milky Way has one, Sagittarius A star. These giants might grow by merging with others or by pulling in vast amounts of gas. Their immense gravity shapes galaxy dynamics and influences star formation. Though black holes emit no light, we detect them by their effects on nearby matter. Astronomers observe X-rays from accretion disks and use radio telescopes to image their shadows. The Event Horizon Telescope gave us the first real image of a black hole in 2019. Some black holes spin, dragging space-time around them, a phenomenon called frame dragging. These rotating black holes, or Kerr black holes, create complex structures and open theoretical possibilities like closed time-like curves, paths that loop through time. The extreme warping of space-time around black holes leads to intriguing questions. Could they be natural time machines? Theoretically, rotating black holes could allow for time loops. However, stability and paradoxes make such travel highly speculative. Still, they remain one of the best candidates for studying time travel. As our ship nears the black hole, the stars begin to twist, and light bends unnaturally. The gravity is so strong, even the view of space distorts. This is gravitational lensing, where space-time bends light like a lens. The closer we get, the more reality begins to warp. Time outside races ahead. A minute for us could mean years for Earth. Near the event horizon, time stretches. The ship's clocks seem normal to us inside, but outside, years might pass in seconds. This isn't science fiction, it's Einstein's relativity in action. This stretch of time means that potentially, we're stepping into the future simply by hovering near this cosmic abyss. Get too close, and you feel the difference in gravitational pull between your head and feet. This is called spaghettification. You'd be stretched into a thin thread. This happens because gravity near a black hole isn't uniform. The tidal forces are so intense that they can rip atoms apart. Hovering just above the event horizon, the ship's systems go haywire. Signals scramble, and instruments drift into chaos. But it's also the perfect spot for studying the black hole's effects on light, time, and matter. We send out drones to skim the boundary, collecting precious data for Earth. At this strange boundary, light itself can orbit the black hole. The photon sphere is like a circular racetrack for photons. From our perspective, the ship reflects ghostly images of itself as light makes laps around us. We're surrounded by our own visual echoes. Crossing the event horizon, we enter the zone of no return. From Earth's view, we freeze in time, but from our perspective, we move smoothly forward. Outside communication ends. We are now inside the most extreme environment in the universe, the domain of warped time and gravity. Inside the black hole, no signals can escape. Stars vanish behind us. Only darkness and the curvature of space remain. We are cut off from the universe. Navigation fails. Space twists so extremely that directions lose meaning. Forward is inward now, toward the singularity. As we descend, the laws of physics begin to blur. Matter stretches, time behaves strangely, and space curves infinitely. Concepts like before and after lose meaning. Some theories suggest alternate realities or parallel timelines could branch from this point. We are past the limits of conventional science. We're approaching the singularity where density becomes infinite. All calculations break down. Space shrinks and gravity becomes absolute. In this final stretch, we may gain profound insight or simply cease to exist as we understand it. This is the deepest point of time distortion. At the brink of the singularity, a second for us might stretch into an eternity outside. If we could observe Earth now, entire civilizations might rise and fall in what feels like a blink. We've become travelers through time, not by speed, but by falling into infinite gravity. Is there a way out? While physics breaks down at the singularity, some theories suggest paths might exist, like wormholes or quantum tunnels. These might connect distant regions of space or time. It's speculation, but in these extreme zones, the impossible becomes less impossible. A wormhole is a hypothetical bridge connecting two separate points in spacetime. Think of it as a tunnel with two mouths. If stable, it could allow faster-than-light travel or time travel, but creating or surviving one would require exotic matter with negative energy. Physicist Kip Thorne explored if wormholes could act as time machines. If one mouth moved fast or sat near a black hole, time between them could become offset. Step into one end, emerge in the past. But paradoxes and stability make this largely theoretical. Time travel to the past invites paradoxes. What if you went back and prevented your own birth? The grandfather paradox questions whether changing the past creates contradictions. Does the universe allow these changes or correct them? One solution to paradoxes is the multiverse theory. Each choice creates a new branch of reality. Time travel doesn't change your past, it creates a new one. You'd enter a parallel universe where your actions diverge. In the block universe view, past, present, and future already exist. Time is like a landscape. We just experience it slice by slice. If true, time travel would be more like moving across space, but everything is predetermined. Some physicists argue time isn't real at all. It's just an emergent property of quantum states. The universe may be timeless at its core, and before and after are simply perceptions within our consciousness. Time travel to the future is real and already happens. High-speed astronauts, GPS satellites, and even people on mountaintops experience time slightly differently. But to leap far into the future, you'd need extreme speed or gravity, like orbiting a black hole. Light from distant galaxies shows us the past. When we look into space, we look back in time. Telescopes act as time machines, revealing stars and galaxies as they were billions of years ago. The universe itself is a vast time capsule. Even if we can't return from a black hole, information might. Hawking radiation suggests black holes slowly leak energy and information over time. This could help preserve the story of what falls in, possibly including timelines or travel logs. In some theories, closed time-like curves allow for stable loops in time. An event could be both cause and effect, like giving yourself a notebook from the future that helps you build the time machine that sent it. These loops challenge our ideas of cause and consequence. Could time travelers walk among us unnoticed? If they came from the far future, maybe they'd blend in or manipulate events subtly. While no evidence exists, the idea fuels both science fiction and serious scientific thought experiments. If time travel were possible, should we use it? Changing the past could erase lives. Visiting the future could destabilize economies or society. Like nuclear power, time travel could be dangerous in the wrong hands, or an incredible force for good. Eventually, all timelines converge, whether in a singularity or through entropy. Time's arrow always points toward higher disorder. Even if we travel, we're still part of this universal story. The loop may close, but the journey changes us. Perhaps time is not a straight line or a circle, but a story still being written. What we see as endings may be doorways. And if the universe allows, the final second of our journey could become the first second of something else. Once you cross the event horizon, there's no turning back. Light can't escape, and all paths lead toward the singularity. But what would it feel like? Surprisingly, you might not notice crossing the boundary, at least not instantly. The real drama comes closer to the core. Inside a black hole, the difference in gravity between your head and feet could be trillions of times stronger. This tidal force stretches objects into long, thin shapes, a process called spaghettification. It's not survivable, but fascinating. Some physicists propose a firewall, an invisible barrier of high-energy particles at the event horizon. If real, anything hitting it would be instantly destroyed. This controversial idea challenges Einstein's predictions and fuels debates about what really happens at the edge. Near the singularity, general relativity breaks down. We need a new theory, a quantum theory of gravity, to understand what happens. Candidates like loop quantum gravity or string theory attempt to unite gravity with quantum mechanics. Stephen Hawking theorized that black holes aren't truly black. They slowly emit radiation due to quantum effects. Over unimaginable timescales, this radiation causes black holes to evaporate. Even the biggest ones will eventually vanish. When a black hole finishes evaporating, what's left? A burst of energy? A naked singularity? Or nothing at all? We don't know, but this final moment could encode clues about how time, matter, and reality itself are woven together. Black holes influence galaxies, star formation, and cosmic structure. They shape the very architecture of the universe. Even after they disappear, their gravitational footprints remain, cosmic echoes of ancient power. Some scientists believe black holes might birth new universes. Inside the singularity, a bounce could lead to another Big Bang, creating a universe with different physical laws. Our universe might itself be inside a black hole. Time seems to move forward, but why? One idea: entropy. The universe moves from order to disorder. Near black holes, entropy reaches extreme levels, possibly giving us insight into why time flows and can't be reversed. Does information fall into a black hole and vanish forever? That would break fundamental laws of physics. This is the black hole information paradox. Some believe Hawking radiation encodes the lost data. Others think reality rewrites itself. A radical theory suggests our 3D world is actually a projection from 2D information encoded on a surface, like a hologram. Black holes support this idea, storing information on their event horizons. Could reality be a cosmic illusion? If time travel, black holes, and quantum tricks seem strange, maybe it's because we're in a simulation. Advanced beings might simulate entire universes, with black holes as data portals or memory drives. In quantum physics, the observer affects what happens. Time and space may not exist independently of us. They emerge through observation. Black holes might test the limits of what is knowable. Time remains one of the deepest mysteries in science. Is it a loop, a dimension, a story, or an illusion? Black holes help us explore these questions. Perhaps we're not meant to answer them, only to wonder and explore. From Einstein's equations to falling into a black hole, we've stretched our minds across space and time. As we continue exploring, one thing becomes clear. The universe isn't just strange, it's stranger than we can imagine. From the earliest myths to modern science, humanity has always looked to the stars. Time, space, and black holes aren't just scientific puzzles, they're part of our story. Curiosity drives us to ask, what lies beyond? Imagination gave us time machines long before science caught up. From H.G. Wells to Christopher Nolan, fiction shapes how we think about time. Sometimes dreaming comes before discovery. New instruments like the James Webb Space Telescope, gravitational wave detectors, and quantum computers push our boundaries. Every discovery about black holes opens doors to deeper questions about time and existence. Someday we might learn to manipulate space-time, not just understand it. If we harness black holes, wormholes, or exotic matter, we could build gateways to other times or places. If time travel becomes real, what are the consequences? Could we change history? Visit the future? Who controls such power? With great knowledge comes great responsibility. We must tread carefully. One day, black holes may be the last surviving objects in the universe. If intelligent life survives that long, could they use them to preserve knowledge? Time may end, but legacy might remain. Despite the science, we all feel time personally, in memories, aging, and anticipation. Time travel may begin not with black holes, but with understanding ourselves. We may never fully understand black holes or time, but that's okay. Wonder is its own reward. It fuels exploration, connects generations, and reminds us that we're part of something vast. Imagine sending a message into a black hole, not to retrieve it, but as a symbol of hope. Like time capsules, it would say, "We were here. We tried to understand." Time, travel, black holes, they're not just concepts, they're keys to the deepest truths. As we gaze into the unknown, we carry with us the most powerful force in the cosmos, curiosity. The journey never ends.